Hi everyone, this is the second video for section 7.1, an introduction to decimals. So in this video, we're going to start off with talking about how to use base blocks to model decimals. So we've used base blocks mostly in chapter 3 to model whole numbers, but we can also use decimals to represent that. So for just a basic example, we can have a flat represent a value of 1. So then when we have a flat, okay, sorry, one thing to note here is that all of these representations of decimals using base blocks will be using base 10 blocks. And that's because what we talked about in the last video, that all of our decimals are going to be denominators that are powers of 10. So all of these are going to use base 10 blocks. Because if a flat represents a value of 1, then each flat has 10 longs. So a long will represent the value 1/10. And each long will then have 10 units. So a unit will represent the value 1/100, so 1/100th. And we can do it in this way. So if we have a flat representing a value of 1, then a long is 1/10 of that, and a unit is a 10th of a long, which is a 10th of a 10th. And so based off what we know about multiplying fractions, that is 100th. And so this isn't the only way to do it. We could also have a different block represent the value 1. For example, we could have the 1000th cube. So let me just draw up here what these look like. So we have a unit, a long, a flat, and then we have this cube. So this cube is going to come up a little bit more now that we're just dealing with more places. So this is, the book calls it a big cube. I'm just going to call it a cube. It's the cube, so it represents the thousands place. So if our unit is our ones, our long is our tens, on our flat is our hundreds, then our cube is our thousands. But we can also do it the opposite way. So if our cube is our ones, then our flat is our tenths, our long is our hundredths, and our unit is our thousandths. So it can go both ways, like so, just instead of going up from units, going down from cubes. Okay, so we want to write the number 14.32 in expanded form. And so this expanded form is going to be really similar to the expanded form that we had before. So 14, oops, I'm gonna do this in black. So 14.32 is going to be, well, the whole number that we have here is 14. So 14 is represented by 1 times 10 to the first plus 4 times 10 to the 0. That's how we get our 14. And then we just do the same thing to get the 0.32. So you see how whenever we write things in expanding form, our powers of 10 were decreasing. So we had 10 to the first followed by 10 to the 0. Well, we just keep decreasing and that pattern continues. 3 times 10 to the negative 1. And then 3 times 10 to the negative 2. Oh, sorry, 2 times 2. 2 times 10 to the negative 2. So we can just keep decreasing this exponent, which I think the easiest way to write this out at first is to just write it with the exponent. You can also you don't have to write it with the exponents, right? Like we saw in this table up here, the exponents are the same thing as just writing it as the fractions or the expanded exponent. So we can do that same thing down here. So this is 1 times 10 plus 4 times 1 plus 3 times 1/10 plus 2 times 1/100. And so the expanded form just works just like before. One thing to note that in the book, it has this written a little bit differently, where it goes ahead and combines the multiplication within each of these sets of parentheses. On any sort of exam, That is not how I want you to write it. If I tell you to write something in expanded form, I think it's just easier to stay consistent and go ahead and write it all out in this form. Okay, so I know we don't have a lot of space, but I want to go ahead and use base blocks to model 14.32. So we're always going to have our unit size represent the smallest place value that we have. So the smallest place value we have is that 2. And that 2 is in the hundredths place. And then we have 4 total place values. So the 1, so this 2 is going to be 2 units. So we have 2 of these units. And this is another reason why I refer to these just by the names unit, long, flat, and cube, rather than 1, 10, 100, 1,000, because they represent different things, especially when we talked about different bases, but even now here when we're doing decimals. So we had 2 of the units, and now we'll do 3 of the longs. We'll do 4 of the flats. And that tells us that this flat is representing the ones place because we have 4 of them. And then lastly, we have 1 of the cubes because the cube here is going to, well, let me draw a little bit. It's going to represent the thousands place. Okay, in here, so one thing that I set up here, when using base blocks with decimals, you must indicate what block represents 1. So this is one of the most important parts. So we have down here that this flat represents 1 because we had, oh, I should have had 4 of those. My apologies. Let me erase this cube because I should have had 4 flats and then 1 cube. Okay, so the flat represents 1. We have 4 of them. We have 1 that's 1 unit bigger. We have 3 that's 1 unit smaller and 2 that are 2 place values smaller. Okay. So yeah, sorry this was a little bit cramped up here, but this is how you would do it. Where, again, whatever your smallest place value is, just pick that to be represented by the unit, and then you can just work your way up from there. Okay, so now we're going to talk about terminating decimals. So there are really just 2 different types of decimals, terminating or non-terminating. So you may have heard this as repeating and non-repeating, where a repeating decimal or a non-terminating decimal is just something like 1/3, which is 0.333333 forever and ever. It doesn't terminate. Essentially is all we're dealing with. It's something that doesn't terminate. It has an infinite number of digits after the decimal point. And we have this nice little theorem that tells us when a fraction will result in a terminating or non-terminating decimal. So it says that when a fraction is in simplest form, it can be written as a terminating decimal provided that the prime factorization of the denominator contains no primes other than 2 or 5. And, well, you may look at this and say, why the heck do I just care about 2 and 5? Well, that is because our denominator, so I'm going to tell you, our denominator must be in multiples, well, not multiples, but powers of 10 is how we've defined decimals. So rather, let me think about the denominator. So in order for us to get a nice fraction, our denominator must be in a power of 10. And 10 only has the prime factors 2 and 5. So that means if we want to make our denominator, so for example, say we're given the fraction 4/25. And in order to write this as a decimal easily, we want our denominator to be a power of 10 because whenever we looked at this table, all of our denominators are powers of 10, 1/10, 100th, 1000th, and so on. So we want our denominator to be in a power of 10, but we know that 10 only has prime factors 2 and 5. So in order to make this a power of 10, well, we know that if we multiply 25 times 4, we can get 100. And so we'd say that this is 16 over 100, so it can be represented by the decimal 0.16. But that's only possible because this is also written as 4 over 25 is 4 times 5 squared. The prime factorization of the denominator only has 5s, and so in order to get it to be a power of 10, well, we just have to add 2 2's. So we multiply by 2 squared over 2 squared. So we get 4 times 2 squared on the top and 2 times 5, which is 10 squared on the bottom, right? We have this property of exponents. Well, let me rewrite that a little bit. Where if we have bases raised to the same exponent, we can just multiply them together. So we have it like this. And that's 10 squared on the bottom, which is exactly the same thing we have above, but it happens for this reason of the prime factorization. Okay, so in order for a fraction to translate to a terminating decimal, the denominator has to only have prime factors 2 and 5. But there's one other part of this theorem that says the fraction has to be in simplest form. And so why is that the case? So the fraction must be in simplest form because otherwise this doesn't look that nice. Let me rewrite this a bit. Fraction must be in simplest form because otherwise some prime factors may not cancel out. Like they should. And so this may best be explained with an example. So if we consider 9 over 12, well, this fraction is not in reduced form because if we look at the prime factorization of the numerator and the prime factorization of the denominator, we have 3's in common on the top and on the bottom. So whenever we look at this, well, we say, well, we have the prime factorization of the denominator has 2's and 3's, right? It's not 2's and 5's, so that means that this isn't terminating. However, if we were to cancel out one of those 3's, then we would see this is the same thing as 3 over 2 squared. And now that 2 squared does just have the prime factorization with 2's and 5's, so we can multiply by 5 squared on top and bottom. And we can get this is 75 over 100. So this fraction that we started with, 9/12, even though the prime factorization of the denominator does not just have 2's and 5's, well, if we convert it to simplest form, then it does. And then we can see that this is 75 over 100, which is just a nice terminating decimal, 0.75. Okay, so that's about all I had to say for terminating decimals. There's more examples in the book on page 249, but in the next video, we're going to start talking about ordering decimals on a number line.